All right, hello again. This is Jeff Scott, your instructor for 152, 145 Advanced Java Programming for the fall 2015 semester. We're in Chapter 15 of 16 in our Java book, and this chapter is on recursion. And in this chapter, I'm going to go over this and go over what's in the book. No homework on it, no examples, no anything. So let's just get started. All right, we get an introduction to recursion, talk about how to solve certain problems with recursion, give examples of recursive methods, talk about a recursive binary search method, and finally try to solve the kind of classic Towers of Hanoi project or problem with recursion. As it says, so far we've always been calling other methods from a method. So you've got method main calls, maybe, for instance, if we were doing a program that was creating an array and in that array we were going to put a bunch of stuff in it, like, find the biggest value, the smallest value, then we might have main call a routine to fill the array. We might have main call something to get the biggest value, the smallest value, the sum and average of the values, etc. But it's also possible, as mentioned right here, for a method to call itself. When a method calls itself, it's known as a recursive method. All right, so the example that they show in the book, and we'll go over that in a little bit, as it says, just says this is a recursive method and it keeps calling itself. So typically, if you're going to use recursion, there's a couple things about it. Number one, you better find a way to stop the method from calling itself unless you want it to call itself infinitely. That's the first thing. And secondly, virtually any problem that is solved with recursion can be solved without using recursion. The disadvantage of using recursion is it tends to really slow down program execution time. So they give an example here where they say they want to call this thing 6 times basically. So that it's calling itself, but while it's doing it, n is the loop control variable, and n is being decremented every time. So when it gets down to 0, it tells it to stop calling itself. All right. Again, some of this I've already said, but I'm going to say it again. Recursion can be a powerful tool, but it's never required. Any problem that can be solved recursively can be solved rather non-recursively, typically using a loop. In many cases, as I already mentioned, recursive algorithms are less efficient than their iterative counterparts. The reason for that is every single time the method calls itself, it has to take and copy all of the variables that it has and put them on the stack. And then as it gets back from that call, it's got to grab those variables again back from the stack. And as it says, these actions are known as overhead, and they take place with each method call. All right, you don't have that kind of overhead within a loop. Some repetitive problems are solved more easily with recursion, but again, typically always. There are some instructors. I had an instructor back when I went to school who just totally did not believe in recursion. And he said never use it under any circumstance. So again, as mentioned there, iterative algorithms might execute faster, but a recursive algorithm might be designed faster. So you might get it up and running faster. It might be less code. But again, typically, it's going to take more time for it to run. So when you work with recursion, as it says, you must establish a base case. And the base case basically tells you when you're done, when the problem has been recursively solved. So if the base case cannot yet be solved, you have to call itself. The function has to call itself again. So the example they give here is they start talking about factorial. And I may have even talked with you about this before, I don't know. But if I say 10 factorial, which is the way that is written, that's the same thing as 10 times, let's use times, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. All right, that's what 10 factorial is equal. But when you look at it, 10 factorial is also equal to 10 times 9 factorial. All right? And 9 factorial is equal to 9 times 8 factorial. Hopefully you can see where we're going here. But just in case, I'm going to go down most of the way here anyway. All right, so we've got 10, 9, 8, 7, 6, 5. Hopefully I didn't miss anything. Let's make this a little smaller so we can see it all on the screen easily enough. And 0 factorial is equal to 1. So what you can see is we're going down here, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 9, 8, 7, 6, 5, 4, 3, 2, 1. So you can see we can use the same algorithm and just keep stepping down as we're going through this. Again, this is an example of using or of a problem that can be resolved recursively. Another famous one is the Fibonacci number system. And it had to do basically with if two rabbits multiply and those two rabbits multiply, etc., 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 how long until you reach a certain amount. So the Fibonacci number system looks like this. Oops. We'll leave it right there. So 0 plus 1 equals 1. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8. And you get the idea. Those are the two problems that are like those are probably the two most oftentimes ones that are described when people talk about using recursion. All right? So there's the factorial thing. So they say the rules state when n is 0, its factorial is 1, and you're done. If n is greater than 0, the factorial is the product of all the positive integers up to that. So 6 factorial looks like this. I did it the other way because that's how I was taught. 6 times 5 times 4 times 3 times 2 times 1. Again, if n equals 0, then the factorial of n is equal to 1. Otherwise, you have to call it, it calls itself again. This is what's important when you work with recursion. The recursive call works on a reduced version of the problem. So here's an example of a Java-based solution. This is the function factorial. If n is equal to 0, or you return 1 because you're done. Otherwise, you return whatever your number was times the factorial of that minus 1. And it's exactly what I just showed you pictorially with the 10 exclamation point, etc., all the way down. So they're showing an example here. All right, it says when recursive methods directly call themselves, it's known as direct recursion. There's also indirect recursion, when A calls B, which in turn calls A again, and there can be intermediates in there. So as it says, A can call B, B can call C, and C can call A. Care must be used always with any kind of recursion. I'm not disagreeing with what the author says here, but anytime you come up with a recursive solution, you better make sure eventually you stop. So here is an example where they talk about recursion to use it to sum a range of array elements. So you've got what? Some kind of an integer, that's an array. And you want to show the start of the array, the starting element, and the ending element. So that's 0, 1, 2, 3, 4, 5, 6, 7. So 0, 1, 2, 3, 4, 5, 6, 7. So you'd be able to add up all those array elements as an example. There's another one in here for drawing concentric circles, so circles within circles. This is the Fibonacci one that I've already mentioned to you. You can see, I think I did it right. Let's just take a quick look. Zero, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. They went a little further than I did. Pretty simple algorithm. If n equals 0, return 0. Otherwise, if it's 1, return 1. Otherwise, just keep it, basically add the previous one and the current one, the two previous ones to get the current one. Here's another one with the greatest common divisor. If you've never seen that before, so if I have the numbers 6 and 8, what's the smallest number that goes into both 6 and 8? Well, it's 24. Okay. Finally, they end up talking about a recursive binary search. So as it says, if the middle equals your search value, you're done. Otherwise, if it's less than it, you just check the upper half. Otherwise, you check the lower half. Okay, Towers of Hanoi. We'll take a look at it in the book in just a minute. So that's pretty much it for this. All right, so we'll come back in just a second and we'll talk about the stuff in the book. In fact, let's not even do that. Let's just go over the stuff that's in the book right now, okay? So I'll just combine this into one lecture. I don't see any problem at all with doing that. So again, I'm in Chapter 15 talking about recursion. A recursive method is a method that calls itself. So if we look right here, this would be an infinite loop. Because what is message doing? It's calling itself. Now this semester when I'm working with the first year people, we're using JSBin and we're using the JavaScript runner. We did that for the first assignment to go in and run our JavaScript. Now starting with the second assignment, we're putting our JavaScript in its own file, our CSS in its own file, and our HTML in its own file. And the HTML file has links to the CSS file and links to the JavaScript file. But the point is, when we use JavaScript runner and when we use JSBin to make sure that our program started, at the end, we'd have something like this, but at the bottom, we'd have main call itself. It wasn't a recursive call, though, as you see right here. Now, in this example, it says this is a recursive method, but you only want to do it while n is greater than 0. All right, well, when you run it, we're calling it 5 times. So you can see what the output is. After the 5th occurrence, n is equal to 0. So it says here, this is our base case. If n is not greater than 0, we fall out. Well, it's greater than 0, so for 5, 4, 3, 2, and 1, we print this as a recursive method. We call it again, and now the next time it's 4, then it's 3, then it's 2, then it's 1. Finally, it becomes 0, which is not greater than 0, so you fall out. So they show this pictorially also in here. It gets called 6 times, but basically with the 6th one, after you get done with it, n is 0, so you don't have to go and write this stuff again. So in general, as mentioned here, you can see this about halfway down on the page, right equivalent here with the video note. A recursive method works like this. If the problem can be solved without recursion, the method solves it and returns. If it cannot be solved, then the method reduces to a smaller but similar problem. All right, and when you reach this point where the problem can be solved without recursion, that's your base case. And if it can't be solved without recursion, if it needs to be called recursively again, that's your recursive case. All right? They talk about factorials in here and a bunch of other ones. I already went through the factorial one with you. So they go through the example right here. So again, if I say 4 factorial, all right, what does that mean? Well, I'm going to be typing in 4 times 3 times 2 times 1 times 0 factorial, which is 1. So 4 times 3 times 2, the equivalent times 1, which is going to give us 24. Again, what you'll find is if you run a factorial program and you put a big number in there, like 50, so that's 50 times 49 times 48 times 47. If you have a data type that's big enough to hold that value, you're going to find that it's not going to work nearly as slick or as fast as you think it is because recursive solutions, by and large, are slow. We talked a little bit before about direct and indirect recursion. So if method A calls method B, which calls A again, that's direct recursion. But if A calls B and B calls C and then C calls A, that's indirect recursion. All right, so here was adding your array elements. Okay, so again, notice we're saying 2 through 5. Why 2 through 5? Because we say in here that what we want to do, so that's 0, 1, 2, 3, 4, 5. If I did that right, it should be 18. And you can see there's our output. So we could call this, we could pass in any array we wanted here. We could start anywhere we wanted and end anywhere we wanted. So if we had an array with 100 elements in it, we wanted to find the biggest element out of all 100. Let's just say it was called numbers. We put in numbers. We could start at location 0, and we could end at location 99. The concentric circles, you can take a look at that yourselves. I'm not going to go through that. You end up drawing with the equivalent of like a spiral graph. Back in the day, if you don't know what that is, that just means I'm too old. A Fibonacci number system, this gives you the first 10 numbers in the Fibonacci number system. So again, it'll give you 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. I think it's 283 or something like that. So greatest common divisor, another example. And they end up again with that binary search method. Again, the takeaway from this should be that any problem that you do that you solve recursively can be solved non-recursively. So they talk about in here, the idea is you want to move everything from here over to here. And these are your rules. Only one disk can be moved at a time. Well, you know what you have to start with. All right. So for instance, I'd move this one here, okay? And I'd move it there. Then I'd take the second one and I'd move it here. All right. Then I'd take the first one, or the third one, or the bottom one, and I'd move it, no, the first one I'd move here. So I'd have the first two here in order. Then I'd move the bottom one here. All right. So move disk 1 to peg 2. Move disk 2 to peg 3. Move disk 1 to peg 3. All right. And then they go through and they talk about everything that you have to do to basically move them from here to here. And they kind of go through it pictorially here so you can see what's going on. It's a neat algorithm. It really is. It's fairly simplistic, just to show you what goes on in here. that's it. So I don't normally do this, but let's just take a second because there's only 3 of them and go over this common errors to avoid. Always have a base case. Always reduce the problem with each recursive call. Always write it so that the base case is somehow reached, because if it's never reached, you're going to get an infinite loop. All right? Again, no homework on this one. I plan on giving one more set of lectures, and that will be on Chapter 16 on databases, which I'll get to shortly.